So by the time we finished our last class, you know, we advanced to a certain degree in simple harmonic motion oscillations. We started with a restoring force acting on a particle proportional to displacement from a certain position, in this case x equal to 0. K was the force constant, leading to acceleration equal to force divided by mass, and we defined omega squared as k by m. This a was actually d2x dt2, the acceleration of the particle with respect to time. That's equal to minus omega squared x, right? This was the differential equation associated with simple harmonic motion. Omega was referred to as the angular frequency. The point where the net force was 0 was the equilibrium position or the mean position. In this case, F is 0 at x equal to 0. So x equal to 0 in this case was the equilibrium position. And omega, the angular frequency, defined as square root of k by m, leading to time period as 2 pi by omega. The solution to this equation was x equal to a sine omega t plus phi. Phi was a phase constant. Omega t plus phi was the total phase of the particle, right? Differentiate, and this could have been a cos omega t plus phi. That phi would have then been different. That's all, right? And so on and so forth. So based on this, we also obtained the potential energy at various values of x, the kinetic energy for various values of x. If you remember, the potential energy at any given x was given by half kx squared, where k was referred to as the force constant, fundamental to the oscillating system. A was within our jurisdiction. We could control A, the amplitude. Did I tell you that? That we could control the amplitude, but we cannot control k and omega. We cannot control k and omega. That's innate and fundamental to the system. The potential energy at x is given by half kx square on the premise that at x equal to 0, we would look upon potential energy function to be 0. And the velocity at any given instant of time, or the speed at any given instant of time, was given by omega root a squared minus x squared. And at the mean position, the speed was given by omega a, which is the maximum speed also of the particle, which is also the maximum speed of the particle, leading to the kinetic energy as half m v squared. V squared is omega squared into a squared minus x squared. That's the kinetic energy as a function of x. This is potential energy as a function of x. And the variation, the graphical variation of potential energy with x was given by this. At the mean position, that is at x equal to 0, potential energy was the least. At the amplitude position, minus a plus a, kinetic energy was, potential energy was maximum. And this is how the kinetic energy varied. This is how the kinetic energy varied with x. This is how the potential energy varied with x. Right? This is the variation of potential energy with x. A downward opening parabola is the variation of kinetic energy with x. And the total energy of the system could be looked upon as either potential energy at the extreme position or kinetic energy at the mean position. Either way, you know what I'm saying? The total energy of the system, half Ka squared, which is like the potential energy at the extreme position, which will also be the potential plus kinetic at the extreme position, which will also be the total energy of the system anywhere. And or it could also have been looked upon as kinetic energy at the mean position, right? These were two ways of looking at the total energy of the system proportional to the square of the amplitude. So it depends on how much energy you impart to the system at the initial instant of time. That will determine the amplitude, because the total energy of the system is proportional to the square of the amplitude. You double the amplitude, you would require 4 times the initial energy, so that the amplitude could be twice as much, and so on and so forth. Now, we also figured, if you recall, the oscillator to be equivalent to a simpler motion, in the sense, a snippet of this was given to you towards the last class, end of last class, where when I told you that there was a particle executing simple harmonic motion between P and Q. There was a particle executing simple harmonic motion between P and Q. Let's say when this particle P is here, we could look upon an auxiliary particle to be executing a simpler motion, right? While P was executing simple harmonic motion with mean position being the center of the circle, amplitude equal to the radius of the circle, its auxiliary particle was executing uniform circular motion with angular speed omega synonymous with the angular velocity of the oscillator, right? And as discussed and demonstrated towards our last class, that it was simpler to deal with the auxiliary particle on the auxiliary circle than to deal with the oscillator. The oscillator had a complicated motion, whereas the auxiliary particle had a simpler motion, right? And therefore it made sense for us to sometimes, as and when required, migrate to the auxiliary particle, obtain what the auxiliary particle does, and then translate it back to the oscillator. This is what was done towards the end of our last class. I told you how one could find the time taken by the oscillator to go from one position to another by looking at the auxiliary particle, right? Now, see, one important thing. Say there was an oscillator going from, say, let me call the oscillator P, and let's say it's executing oscillations between these two extremes, L and M. Executing SHM between these two extremes, L and M. Say at time t equal to 0, the oscillator was here and was headed leftwards, The oscillator was here and was headed leftwards. In which case, the auxiliary particle could have been looked upon at Q and moving this way with constant angular velocity same as the angular frequency of the oscillator, right? This is important to understand, right? And this is at t equal to 0, where the auxiliary particle was. The oscillator was here, the auxiliary particle was there, right? And this angle then, phi, this angle phi could be deemed to be the phase constant for the motion. This could be looked upon as the phase constant for the motion. Now, t seconds later, t seconds after this, say the particle comes here, headed in this direction. The auxiliary particle, Q, would be here, headed in this direction, t seconds later, at an instant of time, t, right? In t seconds, the auxiliary particle would have described an angle omega t at the center, right? Now if someone says, what is the phase of the oscillator at this instant of time? The moment someone says, what is the phase of the oscillator at this instant, what you do is, you identify the location of the auxiliary particle on the auxiliary circle instant. This is the location of the auxiliary particle on the auxiliary circle, and this angle omega t plus phi is the total phase of the oscillator. Omega t plus phi is the total phase of the oscillator. This is important to understand, right? So when the moment someone says phase of oscillation, phi. Then look at the corresponding particle on the auxiliary circle and identify this angle. At t equal to 0, this angle, that's the phase constant. Phase at time t equal to 0 is a phase constant phi, right? T seconds later, this angle will become omega t, and this entire angle will become omega t plus phi. That's the phase of the oscillator. So instead of dealing with the oscillator, you migrate to the auxiliary particle and obtain the phase of the oscillator, right? Now, what is more important is, yes, sorry? What is more important is, suppose I think of two oscillators. Okay, let me think of two oscillators, each executing simple harmonic motion of the same amplitude and of the same frequency, but differing in phase. In the sense, let's say there was this oscillator 1 and it executes SHM between, say, limits L and M. One oscillator which executes SHM between these limits L and M, right? And at time t equal to 0, this oscillator, call it P1, was at this position. This was the mean position, right? This oscillator executing simple harmonic motion with angular frequency omega and amplitude A. That was the story of oscillator 1, and at t equal to 0, the oscillator was here, and say it was headed leftwards. The oscillator was headed leftwards. Clear? Now, the second oscillator, at the same instant of time, say this oscillator executing SHM between L prime and M prime, right? Between these two limits, same omega, same amplitude, second oscillator, right? And this is the boundedness of the second oscillator. And at t equal to 0, say the second oscillator, P2, was here and was headed leftwards, right? Now, these two oscillations are identical in the sense, we are talking about the same amplitude, we are talking about the same omega. See, these are two fundamental attributes of oscillation, omega and amplitude. So if two oscillations talk about the same omega and the same amplitude, these oscillations are really the same. So fundamentally the same kind of oscillations. But then, where is it that they differ? They differ in their initial conditions. That means at time t equal to 0, where was the first oscillator? At time t equal to 0, where was the second oscillator, right? That is where, see, what we can do is to understand this. That is where, we end up deploying the concept of phase difference between these two oscillations. If the two oscillators are not in the same state of motion from instant to instant, see, in this case, they are describing the same kind of simple harmonic motion, but from instant to instant, they are not in the same state of motion. That means they are not in the same position and they are not having the same velocity from instant to instant. Therefore, their kinematic states are different from instant to instant. And when this happens, we say that there is phase difference between these two oscillations. This oscillation 1 and this oscillation 2 differ in phase. This oscillation 1 and oscillation 2 differ in phase. Question then is, what is the phase difference between these two oscillations? What then is the phase difference between these two oscillations? To understand this, we will deploy the concept of the auxiliary circle. I take this and mentally imagine this to be superimposed over this. And then imagine that they are executing SHM across, mentally imagine that across the same bounds, same mean position, same amplitude, same omega. So then we are talking of the same auxiliary circle for the two oscillations. We talk of the same auxiliary circle for the two oscillations. Let's say this is the common auxiliary circle that I am mentally imagining, right? Now, so at time t equal to 0, oscillator 1 was here, P1, and was headed leftwards, right? And its auxiliary particle was here, call it Q1, and was moving in this direction. Right? You know what I'm saying? At the same instant, oscillator 2, P2 was here, oscillator 2, P2 was here, and was headed leftwards. Its corresponding particle, that is auxiliary particle on the auxiliary circle, Q2 was here and was headed like this. Right? Right? Now, the phase difference between these two oscillations, is then, see, realize that this is the phase for oscillator 2, isn't it? This for oscillator 2, look at the corresponding part on the auxiliary circle, which will determine the phase of oscillator 2. This angle will be the phase of oscillator 2. That means, say, angle P1OQ2 is phase of P2, right? Angle P1OQ1, is the phase of P1. That's how we have defined the phase of oscillation, right? With respect to the corresponding particle on the auxiliary circle, is it not? Right? Therefore, the phase difference between these two oscillators would be the difference in these two angles. That means this would be the phase difference delta phi between the two oscillators. Delta phi would be the phase difference between the two oscillators. Got me? P2. P1OQ2 is the phase of P2. Because for P2, I would look at the corresponding particle on the auxiliary circle. See? This is P2. Where is its auxiliary particle? Q2. Right? This is the radius vector for Q2. This angle will be the phase of Q2. Is it not P1OQ2? Right now? So this is how the phase of a certain particle, you move to the corresponding auxiliary particle and describe the phase of a certain oscillator, right? So the phase difference between these two oscillations is delta phi, is the phase difference between these two oscillations. Clear? Now, if this is the phase difference between these two oscillations, then this is the only thing that the two oscillators differ in. Everything else is the same. Realize that if delta phi is the phase difference found at a certain instant of time, then delta phi will be the phase difference at all instants of time. Why? Because, see, 1 second later, the amount by which OQ2 rotates would be the same as the amount by which OQ1 rotates, because Q1 and Q2 have the same angular velocity. So if we are talking of two oscillators with the same omega, same angular frequency, that means we are talking of auxiliary particles with the same angular velocity. And therefore, if at a certain instant of time, the phase difference between two oscillations is found to be, say, pi by 3, then that remains the phase difference between the two oscillators at all instants of time. Yes? Yes, we can. But then that will be time dependent. Isn't it? That's why it doesn't make sense to define phase difference between these two oscillators with different omegas, because then their auxiliary particles will have, the angular difference will be different at different instants of time. Therefore, it will not be fundamental to the two oscillators. In this case, delta phi is fundamental because it remains the same at all times, right? If omega is the same. Clear? Are you all okay with this? Now, can I wipe this off? Huh? Okay. Now, so you understand what phase difference means, right? Between two oscillations that are otherwise identical, they will differ in phase, which will remain the same at all times, right? Suppose there were two oscillators, one executing SHM between L and M. Say one oscillator starting from the mean position headed rightwards at time t equal to 0. Right? Another oscillator, so this is oscillator 1. Another oscillator, say L prime M prime, executing an identical SHM. Identical SHM means same omega and same A. Right? About O prime, and this oscillator is P2 at time t equal to 0. It's right here. Right? Yes or no? That means at time t equal to 0, both oscillators are headed in the same direction, have the same velocity, are at the same position. Their kinematic states are identical at time t equal to 0. Yes or no? Yes, sir. Right. So if these two are identical, that means if you take this oscillator and you flush it over this, you will not be able to distinguish between the two oscillators. If there was a phase difference, you would have distinguished. You could see distinctly the two oscillators. But now, if you take this and superimpose over this, P1 and P2 would appear to be moving in tandem. This is P1, this is P2. They would always be moving like this together. You would never see them parting out. Right? Now, in this case, the phase difference is 0. Do you realize that? Why? Because think of the auxiliary particle, common auxiliary circle, same radius. Yeah, let me come to that. I'm just trying to be more general on that. Let me have that. Say, so at t equal to 0, they were in the same states and they were headed rightwards, right? Now, the one particle was going this way, the other particle was going this way. Do you realize then that their corresponding auxiliary particles Q1 and Q2 were both in the same state and was moving like this? So what was the difference in the angles between Q1 and Q2? 0. So in this case, the phase difference between the two oscillations is 0. Yes or no? Right? Now, can I wipe this off? Suppose there were two oscillators, identical SHM, right? The motion of this started at t equal to 0, but the motion of this started at t equal to capital T. You know what I'm saying? Yes, yes. The motion of this started at t equal to 0, but the motion of this started at t equal to capital T. T equal to capital T means what? This oscillator would have done this and would have come back to this, headed in this direction, right? In capital T seconds, this is what P1 would have done. It would have executed a full cycle. That's what P1 would have done, right? Right? Now, until then, P2 was non-existent. At time t equal to capital T, the motion of P2 commenced. Right? Now, do you realize that in capital T seconds, this was P1 starting from its mean position, doing this, coming here, doing this, coming here, doing this, and at P1 at T seconds, capital T seconds, right? By the time P1 did a full cycle, what did its auxiliary particle do? Q1 did a full revolution. That means Q1 already described an angle 2 pi at the center. Q1 described an angle 2 pi at the center in a time equal to capital T. The auxiliary particle of P1 in this time described an angle 2 pi at the center. Whereas the auxiliary particle of P2 described 0 degrees at the center. Yes or no? You know what I'm saying? At t equal to capital T, at this instant of time, the auxiliary particle of this described 2 pi radians at the center, and at t equal to capital T, the auxiliary particle of this described 0 radians at the center. So now, is the phase difference 0 or 2 pi? 2 pi. The phase difference now is 2 pi. Phase difference is 2 pi. Right? Phase difference between these two oscillators is 2 pi. Suppose there was a third oscillator, so this was oscillator 2. There was a third oscillator executing L double prime, M double prime, and yes, suppose its motion started after 2t seconds. Now in 2t seconds, this would have described 4 pi radians at the center, and this would have described 0 radians at the center. Right? So what's the phase difference between 1 and 3? 4 pi. What's the phase difference between 2 and 3? 2 pi. Right? Right? But once the motion of P3 commenced, P1, P2, P3 looked identical in all respects. They enjoyed the same kinematic status at all instants of time once the motion of all three commenced. Yes or no? Yes. Right now? So, whether a phase difference of 0 or a phase difference of 2 pi or a phase difference of 4 pi or a phase difference of an even multiple of pi, every time the phase difference is an even multiple of pi, the particles execute the same kind of motion, will have the same kinematic status from instant to instant. If there are two oscillators that differ in phase by 2 pi or an even multiple of 2 pi, make a note of it, it's important. If there are two oscillators executing SHM with phase difference an even multiple of pi, then the two oscillators are said to be in phase with each other. The two oscillators are said to be in phase with each other. Whenever this happens, then the oscillation is said to be in phase. The oscillation is said to be in phase. Yeah, that's what she said. Yes, it's possible. Yes, only in that case, the phase difference between them will not be constant. It will be a function of time. It will be time dependent. Right? So every time the phase difference is 0, 2 pi, 4 pi or an even multiple of pi, the oscillators are said to be in phase with each other. Right? So then they are essentially identical states of motion at all instants. They are in identical states of motion at all instants. So you understand the phase difference of an even multiple of pi, what it means? Now, please let me teach here. I know you are smart, but give me an opportunity to do this service to you. I'm sure I'll be able to generate expectations. Right. Suppose there was this oscillator P1 starting at t equal to 0 and headed to the right. Right? Amplitude A, angular frequency omega. Right? Oscillator 1 say. And say oscillator 2, say P2, the motion of this started at t equal to t by 2 say, at t equal to t by 2. Right? And it was headed in the rightward direction. It was headed in the rightward direction. Okay. Now, let me look at the auxiliary particle implication of this same. Between, say, these two extremes, I am superimposing these two. Right? Now, by the time the motion of this starts, the corresponding auxiliary particle in capital T seconds described 2 pi radians. So in t by 2 seconds it will describe pi radians. Right? Therefore, for when P1 was here, its auxiliary particle Q1 was here at time t equal to 0. Right? When at a time t equal to capital T by 2, the auxiliary particle was here Q1 prime and was headed like this. Yes or no? Yes. Right? That is for P1. Right? That means the auxiliary particle would have described pi radians in t by 2 seconds. The auxiliary particle of P1 would have described pi radians in t by 2 seconds? Whereas, look at P2. At t equal to capital T by 2 seconds, at the initial instant for P2 that is, its auxiliary particle Q2 would have been right here, right, and would have described 0 radians, right? Whereas at this instant of time, the Q1 prime, the auxiliary particle of Q1 was here and was like this. So at t equal to capital T by 2, the auxiliary particle of P2 was here. The auxiliary particle of P1, which was Q1 prime, as I have shown there, is there. And then, do you realize that this angle is pi radians? Pi radians. Therefore, what is the phase difference between these two oscillators? Pi. The phase difference is pi. Yes or no? Right? Which means, look, the first oscillator P1 in a time t equal to t by 2 does this, isn't it? In a time t by 2, the first oscillator does this, right? The second oscillator P2 is right here and is moving to the right, right? So the first oscillator at P1 but moving leftwards, second oscillator at P2 but moving rightwards, and the phase difference between them is pi. When this happens, we say that the two oscillators are out of phase with each other. See, in this case, what's the phase difference? Pi radians. Whenever the phase difference between two oscillations is pi radians, we say that they are out of phase with each other. That means they're at the same position but headed in opposite directions. They're at the same position but headed in opposite directions. That's when the phase difference is pi radians. They are out of phase with each other. They are said to be out of phase with each other. In fact, every time the phase difference is an odd multiple of pi, I want you to examine this. Every time the phase difference between two oscillations is an odd multiple of pi, we say that the two particles are out of phase with each other. When the phase difference is an even multiple of pi, the particles are in phase with each other. The particles then move in tandem if they are in phase. Do you have a very clear notion of what I have said here about the phase? Right now, Weber? Right? Like this? Okay. Okay. He's saying if P2 was headed in this direction at time t equal to capital T by 2 and P1 was here, see now in a time t equal to capital T by 2, P2 is here, P1 is here. Look at their auxiliary particles, they are at the same position, so they would be in phase. If you find their auxiliary particles to be at the same position and moving in the same direction on the auxiliary circle, then you can conclude that the two particles must be in phase with each other. Yes or no? Right? 2 pi. Because that has already described a certain angle. In this case, is it actually 0? Because see, the radius vector corresponding to the auxiliary particle has described a certain angle. Has described a certain angle, right? Now, look at the following. No, the phase difference is not pi. Phase difference is an even multiple of pi. See, if P2 was headed in this direction, P1 is also headed in this direction, then they are in phase with each other. Because see, the location of their auxiliary particles is at the same point on the auxiliary circle. So they cannot be out of phase. They have to be in phase with each other. Realize that? That's important to understand. That's important to understand. When P2 is in this direction. Okay. See, her question is, In a time t equal to capital, this is P1. In a time t equal to t by 2, P1 comes here and is moving like this. Right? In a time t equal to capital T by 2. Okay. For P2, it's headed in this direction. Right? Look at the positions of their auxiliary particles. Their auxiliary particles are Q1 and Q2 like this. Are they not in phase? Will their auxiliary particles not be at the same position at every instant of time? They'll be in phase with each other. See, now, see, one thing that I must tell you is a phase difference of 0, 2 pi, 4 pi, minus 2 pi, minus 4 pi is all the same. Mathematically the same. It will not make any difference. See, if P1 is like this, P2 is like this at t equal to t by 2, do you realize that they start from the same position with the same direction of motion, headed towards the same extremity? They reach their extremity at the same time. Then they come back to P2 at the same time. They go to their rightmost extremity at the same time, come back to P2 at the same time. So are the motions not identical? That means if you place this over this, will you ever be able to distinguish between P1 and P2? Therefore, they are in phase with each other. They are in phase with each other. No, phase difference will not be pi in this case. Phase difference will not be pi because, see, this is flushing together. So phase difference cannot be pi. Agreed. It has traveled t by 2. But phase difference will still not be pi. It will be 0. It will be 0, or it could be looked upon as 2 pi in this case. Huh? Sorry? No, see, it does not make a difference whether it's 2 pi or 4 pi or 6 pi, it's the same thing. That will not make any difference. But, see, the angle that this makes, they make with each other is 0. Phase difference is not pi. Phase difference is not pi. Phase difference will be 0 in this case. See, the important thing is, what I really want to tell you is, essentially, equivalently, the angle that the two radii make with Q1 and Q2. That's it. That will be the phase difference. Okay? Sorry? No, then don't compare it with 2 pi. Don't compare it. What I want to say is, they are in phase with each other. We cannot get very technical about t by 2 then. We cannot get very technical about t by 2. They are in phase is all that we can say then. They are in phase is all that we can say. Okay? Okay. So, suppose at time t equal to 0, this was P1 and was moving like this, and there was P2 that was moving like this. Right? The auxiliary particle for P1 is here, which is Q1. The auxiliary particle for P2, which is here, which is Q2. Phase difference is pi. The angle that these radii vectors make with each other, that will be the phase difference.
Is there any relation between
Kinematic states of these particles? No. No, all that it means is when they arrive at the mean position, they would arrive at the mean position at the same instant but headed in opposite directions. This is what it means at all times. You would see them at the mean position together but headed in opposite directions ever after. This is what it means. At the same time, while P1 reaches the leftmost extremity, P2 will reach the rightmost extremity. That is what would happen. And then they come back to the mean position at the same time and would be headed in opposite directions. They are out of phase with each other.
They become coincident only at the mean position.
They meet only at the mean. No, see, in this case, realize, think of it. This way, this way, this way, this way. Do you see them meeting anywhere else at any other time? Obviously not. Obviously not. No, their kinematic state. See, kinematic status is determined by not just their positions, but also their velocities. Their speeds are the same at the mean position, but their velocities are different. Because their direction, kinematic status is about position and velocity. They should not only be at the same position, but they should also bear the same velocity. That's when we say that their kinematic status is the same. Their kinematic status, had it been the same at all times, their phase difference would have been an even multiple of pi. They would have been in phase with each other. Yeah, magnitude of course will be the same. Omega A would be the speed at the mean position at all times. Phase difference is pi. See, the initial radius vector, and the angle between them is pi. While the auxiliary particle of this covers the upper half of the circle, the auxiliary particle of this covers the lower half of the circle. That is what it does, right? At all times, there, yes. No, when did I say their phase difference is changing? Their phase difference is remaining constant, is pi at all times. At an instant later, while Q2 would have come to Q2 prime, Q1 would have come to Q1 prime, rotating the same amount of an angle and therefore maintaining the same pi at all times. When did I say phase difference is changing? No, matlab that it is. But what has that to do with the phase difference? Phase difference will still remain pi. Their kinematic states is changing, isn't it? If their kinematic state didn't change, they would be stationary particles. Right? Got me? It's important to understand what in phase and what out of phase means really. You must keep this view intact. Okay? Now, see, this notion would be very useful when we come to, let's say, simple harmonic motion applied to wave mechanics. So you know this notion of phase difference, phase constant, etc. would be very, very critical when we start to learn wave mechanics. So be very sure about everything that I have communicated here. I told you in the last class, this was a spring in its natural state, an ideal spring in its natural state, and a mass m connected to the end of the spring. This is the natural state, unelongated state of the spring. Okay? And connected to a spring, ideal spring of force constant K, and lying on a smooth surface, lying on a smooth frictionless surface. Now, so this is like an equilibrium position for the mass m. This is like an equilibrium position for the mass m. Now, if very slowly I pull the mass to the right by a certain amount x naught, I pull the mass slowly to the right, very slowly to the right by an amount x naught, then the spring exerts on the mass a force kx naught, which is proportional to the displacement x naught of the mass from the mean position or the equilibrium position. Therefore, you can conclude that the motion is simple harmonic. Right? Now, when I pulled it very slowly by an amount x naught to the right, then the amplitude must be x naught. Why? Because if I have pulled it very slowly to the right, then the velocity of this must be 0 here in this extreme position. right? Now if the velocity is 0 here, it really means that this must be an extreme state. This must be the mean position, and the separation between an extreme state and a mean position must be the amplitude, which is x naught. Right? If I pull it very slowly by an amount 2x naught, then the amplitude would be 2x naught, right? Let's say if I pulled it by an amount at any given instant when the mass is x units from the mean position, the force could be described, force acting on the particle could be described as minus kx. Since it's leftwards, the minus sign. And directed towards the mean position, therefore restoring. K is the force constant of this motion. Acceleration then would be minus k by m into x. So omega of this motion would be root k by m. The time period of this motion would be 2 pi by omega, which is 2 pi root m by k would be the time period of this motion. Right? That means whether you pull it initially by x naught or 2x naught or 3x naught, the time period will not depend on what kind of an initial elongation you build in the spring. Time period will be fundamental to the system. Realize that it involves only fundamental facts. K, the spring constant, m, the mass of the particle. And this cannot be tinkered with, right? Until and unless you are brutal with the mass of the spring, you will maintain the same k and you will maintain the same mass m. So you have no handle over t. You have no handle over t, right? But you have handle over the amplitude x naught of the particle, right? Now, suppose, can I wipe this off? I had a situation like this. This was a particle initially at rest. Spring was in its natural state. Okay. And I applied a force F on this, a constant force, say F naught was applied on the particle. So is this an equilibrium position for the particle? No. Why? Because the net force, spring force is 0, but the net force is F naught. So this is no longer an equilibrium position. This is just some position for the particle. This is not an equilibrium position. Do you realize that? Now, particle starts from rest and has an initial acceleration a naught, which is F naught by m. Starts from rest but has an initial acceleration to the right, which is F naught by m. Yes or no?
Yes, sir.
Right? So the particle starts to develop a rightward velocity. The spring therefore begins to elongate. Right? The spring force therefore begins to grow. Right? The external force remains the same. As more and more elongation is built into the spring, the leftward spring force will continuously grow, proportional to the extent of elongation you've built into it, whereas F naught remains the same. That means the rightward acceleration will decrease because it's retarded by the leftward spring force, which is increasing in magnitude. So the acceleration to the right will decrease. But there still is an acceleration to the right. The particle moves to the right. At some instant of time, the particle comes here. And at that instant of time, say x equal to x naught, force F naught to the right, spring force becomes kx naught, such that the spring force is exactly balanced by the externally applied force. F naught is kx naught is this position. The net force is 0 in this position, therefore this should be looked upon as an equilibrium position. So this is not the equilibrium position for this motion. The equilibrium position is this. This is the equilibrium position for the motion, right? Where the in the earlier case, this was x equal to 0, which was the equilibrium position, x direction. Now the equilibrium position is not x equal to 0, but x equal to x naught, which is F naught by k. Which is F naught by k is the equilibrium position. Clear? Now, from this point to this point, do you realize that in this regime, external force has been greater than spring force? Right? Therefore, the particle has continuously got accelerated in this regime. That means velocity of the particle must have increased from, say, O to P, from O to P, from O to P. The velocity of the particle must have increased from O to P, right? This is the position where F naught becomes equal to the spring force. Now, from this point onwards, the external force remains the same, but the spring force grows. So, if you go past this position, past the equilibrium position, then the spring force becomes larger than the externally applied force. Therefore, the particle will begin to retard. The particle will begin to retard, right? So, say, when the particle comes to this state, some x equal to x, this is x, right? This is the origin, this is x. When the particle comes to this x, this is F naught, the spring force is kx, right? What is this length? This length is x minus x naught. Displacement from the mean position is x minus x naught. This is the mean position, and its displacement is x minus x naught from the mean position. Now, the force acting on the particle is what? The force to the left acting on the particle, right? The net force now acting is to the left, and it's going to be kx minus F naught. And therefore, it's a restoring force. Since it's to the left, it's restoring, right? But what is F naught? F naught is kx naught. F naught is actually kx naught, where x naught is the equilibrium position, right? So this is k x minus x naught, k x minus x naught. That means force acting on the particle proportional to the displacement from the mean position. X minus x naught is the displacement from the mean position. Force restoring because it's to the left, proportional to displacement from the mean position, and k is the force constant. If k is the force constant, then the omega of this oscillation must be root k by m. Motion is simple harmonic. Why? Because 1, the force is restoring in character. 2, it's proportional to how far the particle is from the mean position. Therefore, the motion must be simple harmonic with the force constant for oscillation being k. Therefore, omega would be root k by m. The time period of oscillation is going to be 2 pi by omega. Sounds all right? In fact, an algebraic description of the net force acting on the particle, if I have to write an algebraic description of the net force acting on the particle at x, the force at any given x, taking rightward positive, leftward negative, is going to be minus kx plus F naught. Minus kx plus F naught. Isn't it? The algebraic force acting on the particle, F naught minus kx, the rightward positive, leftward negative. So what if this net turns out to be negative, which means net leftwards towards the mean position? But this is the algebraic description of the force. So a force description of this kind also represents simple harmonic motion. I told you in the last class, F equal to minus kx plus c will represent simple harmonic motion, with equilibrium not being x equal to 0, but with equilibrium being x equal to c by k. So in this case, the equilibrium would be F naught by k. The value of x for which this becomes 0 will be the equilibrium position, right? So equilibrium position will be given by Fx equal to 0, means F naught by k will be the equilibrium position, right? So if someone gives you a description of this kind, an algebraic description of this kind of one-dimensional force acting on a particle, then you can readily conclude that the motion is simple harmonic. 2, force constant of oscillation is k. Equilibrium position is F naught by k, not the origin, right? Now, okay, no. I mean, x is a variable position. The amplitude is not dependent on the variable position. It's the rightmost extremity, right? So one thing we have figured out, the equilibrium position, which is x naught by k. Now, yeah, you're right, it will also be the amplitude, x naught will be the amplitude, because see, this is the position of rest for the particle, therefore this must be an extreme position, this must be an extreme position, this is the mean position, and the separation between an extreme position and the mean position must be the amplitude of motion. Yes or no? Right? So x naught in this case must be the amplitude of motion. X naught is f naught by k. Now, let's also figure out, let's say, the rightmost extremity, just to ensure that whatever we are doing is right. Let's say this is the rightmost extreme for the motion. Right extreme. Okay? And this happens at x equal to x. And in the rightmost extreme, what would be the velocity of the oscillator? 0. We expect x to turn out to be 2x naught, isn't it? This is x. We expect it to be 2x naught, because x naught is the amplitude. This must also be the amplitude x naught of motion. Clear? Now, between this position, let's say, A, and this position B, let me apply work energy theorem. Let me apply classical work energy theorem between states A and state A and state B, which are the two extremes, right? We'll apply classical work energy theorem between A and B. Okay. What's the work done by F naught? F naught x, right? F naught into x, work done by F naught is going to be F naught into the displacement x. Right now? What are the other forces acting on it? Spring force. What's the work done by the spring force? Minus half kx squared, negative of the change in elastic potential energy, right? That's the work done by the spring force, negative of the change in elastic potential energy. Elastic potential energy is 0 here and is half kx squared here. And negative of that change would be minus half kx squared. So minus half kx squared. And this must be from work energy theorem, change in kinetic energy. What's the change in kinetic energy? 0. It starts from rest and goes to rest. 0 change in kinetic energy, right? So, x then turns out to be 2f naught by k. But f naught by k was x naught. So this is 2x naught. Just a quick check. That was just a check, right? That was 2x naught, right? So the amplitude of this motion would be x naught to the left of this equilibrium position. It moves x naught to the right of this equilibrium position. Angular frequency will remain root k by m. Irrespective of where the equilibrium position was, irrespective of what the amplitude was, the angular frequency will remain root k by m. This particle will execute SHM about this p. It will go x naught units to the right, x naught units to the left, with angular frequency this, with time period equal to 2 pi by omega, 2 pi root m by k. Right? Right? You're right? Yeah. You see, full cycle means it could start anywhere, but it has to come back to the same point with the same direction of motion. That's all. So it could have done this. That's 2 pi by omega. Or you imagine it here. It could have done this. That's 2 pi by omega. Or you could imagine it starting from here and doing this. That's also 2 pi by omega. All of that is a full time period. Right? So far so good, right? All of you understand this? So one thing for sure, every time you have f equal to minus kx, that is a equal to minus omega squared x, or F equal to minus kx plus c, or acceleration equal to minus omega squared x plus a constant, then you can, in each of these cases, you can conclude that the motion is simple harmonic with the coefficient of x and acceleration being omega squared. Or in the force equation, the coefficient of x being the force constant k. Clear? Now,
for particle to exhibit SHM, it must satisfy two conditions: F is equal to minus kx and acceleration minus omega squared x.
I mean, they are the same actually. Writing F is minus kx or A is minus omega squared x is the same, because the force equation, when you divide by the mass, you get A is minus omega squared x. It's the same thing. Are you in sync with me? Okay. Let me now look at a vertical spring. This was a horizontal spring. Let me now look at a vertical spring. Okay. Ideal spring in all these cases. Ideal spring in all these cases. Okay. This is a spring with a mass m attached to the end of the spring, and this is the natural state or the unelongated state of the spring. Natural state or the unelongated state of an ideal spring of force constant k. Okay? And I am holding on to this mass. I am giving it support. Okay? Now what I do is, very slowly, I let my palm go down, right? If I let my palm go down, then do you realize that this mass will very slowly move down? Because it's a spring, it will elongate, right? Very slowly, velocity of the mass remains 0 at all times. Is it not? Yes, sir. Right? So after a while, so in this case, two ways of doing this. One, I could have moved it down, rendering it support at all times, and then at some point of time, initially, see, the mass is very helpless. Very helpless. It's itching to elongate the spring, but the palm is preventing it from doing that. But then, it could go down if the palm is moved down. If the palm obliged, it would go down, right? And eventually, the spring also elongates. At some point, where the velocity of the mass remains 0 at all instants, the spring force, the spring elongates by an amount x naught. The spring elongates by an amount x naught. This is x equal to 0. Where the spring force kx naught just about balances the mass, the weight, just about balances the weight. Isn't it? Right? At that point of time, it's like a child being groomed. Initially, you give it support, and when it's capable of handling it all by himself, you withdraw the support. At this point of time, you withdraw the support, and the mass will remain in equilibrium. Yes or no? The mass will remain in equilibrium. So this is an equilibrium position for the mass m. This is an equilibrium position for the mass m, where kx naught has balanced mg, the weight of the product that you are grooming has taken care of the external influences kx naught. Okay? Now, this is the position that you have left the mass with. What will happen to the mass? So this is, say, this was the natural state, x equal to 0. This was the state x equal to x naught, an equilibrium position or the mean position for the mass m. What will the mass do if left in this state? Nothing, yaar. Why? Why would it do things unnecessarily? It will remain in equilibrium. It has zero velocity. It will maintain zero velocity. Zero acceleration, so it will maintain zero velocity, right? However, next, this was a mass groomed by you. You brought it to this state, and now you want it to be in motion. You don't want it to be static all life, right? So what you do is, you say, all right, I want to impart it some kind of motion. Very slowly, I pull it down by an amount. Say x. I pull it down by an amount x. Not from here, from the natural state. Yeah, I'll discuss that after this. Right after this, I'll discuss the case where I'm brutal with the mass. Okay. I mean, right now we are not giving stepmotherly treatment to the mass. We are, right? Next we'll give the mass a stepmotherly treatment and see how the mass responds with the stepmotherly treatment, which is like withdrawing the support abruptly. Right now, I've not withdrawn the support abruptly. We groomed it to the state and then let it go. It remained in equilibrium, happy. Okay, and now I said, well, it's not good for the mass to stay so happy. Very slowly I pulled it down by an amount x. This was the equilibrium position. Now, realize that in this state, when the mass was displaced by an amount x, not from the equilibrium position, but from x equal to 0, the force acting is kx upwards and weight mg downwards. Right? So the net force acting on the mass is what? F upwards. The net, which is a restoring force. If a force is directed towards the equilibrium position, that's a restoring force. The magnitude of this restoring force is going to be kx minus mg. Hey, but what's mg? mg is kx naught. mg is kx naught. So this is k x minus x naught. Right? Hey, what's x minus x naught? It's displacement from the mean position, yes or no? X minus x naught is the displacement of the particle from the mean position. So force acting, restoring force acting on the particle, proportional to displacement from the mean position. The force constant for this oscillator is k, right? The force constant for this oscillator is k, right? So the omega of oscillation is going to be root k by m. The time period of motion is going to be 2 pi by omega. And so on and so forth, right? Motion is simple harmonic with x naught being the equilibrium position. Now, what about the amplitude of motion? Hey, suppose you brought the particle to an equilibrium position here, right? Zero velocity, but this for sure is a mean position. This for sure is a mean position. But now you are pulling it down, and you know for sure the particle will execute simple harmonic motion with omega equal to root k by m. Now very slowly you pull it down by an amount 10 centimeters. Very slowly. So what will be the velocity of the particle here? 0. Because it's being moved down very slowly, it maintains 0 velocity. So this must be an extreme state of motion. Therefore, this must be an amplitude position. This must be an extreme state or amplitude position. This is the mean position, and therefore, this 10 centimeters that you have built into the particle must be the amplitude. What would be the omega? Root k by m. Time period 2 pi by omega. Next, some other Johnny comes down and pulls it with 20 centimeters. What would be the amplitude? 20 centimeters. What would be the omega? Therefore, since you groomed the particle to its equilibrium state, you rendered its support all the way to equilibrium, it gives you an option of imparting it the amplitude you wanted to. You could give it 20 centimeters, 30 centimeters, 5 centimeters, 6 centimeters. Does not matter. It will let you impart the amplitude you want to in this case. Omega, however it reserves for itself, it's going to be root k by m. Right? No, it's not an extreme position. X equal to, oh, this is an extreme. Yeah, so it will go here. In this case, see, if it has been moved down by 10 centimeters, doesn't mean that this will be an extreme state anymore. Because now you start with this. It will not be an extreme state anymore. If it could go up, compress the spring, that will be the uppermost extreme that could happen. This will no longer be an extreme state. But why? That's what I'm saying. This is not the amplitude position anymore. If you have elongated it by an amount 10 centimeters and let go, then it will go 10 centimeters above this. It may not coincide with this. No, it may not be equal to x naught. Yes. No. No. It's not because of the palm that x naught is the mean position. Even if I abruptly withdrew support, this will still be the mean position because it has to get displaced by an amount x naught for it to balance mg. So that has not, the equilibrium position has nothing to do with me. But the fact that I brought it to the equilibrium position that was desired, that it was meant to be, that it respected me for the amplitude I imparted. I could then give it any amplitude I want to. 10 centimeters, 15 centimeters, 6 centimeters, 11 centimeters, and this is the lowermost extremity, but this is not necessarily the upper extreme.
So if we impart an amplitude such that it goes on to compress the spring.
Yeah, it could do that. It could do that. Suppose 10 centimeters is more than x naught, then it will compress the spring. It could. The only thing is it will compress the spring to such a degree that eventually its velocity will be rendered 0. Perfect, it's possible. It's not like, it has to acquire an extreme state only in the natural state of the spring. No, there is nothing of that sort.
So, how do you impact the amplitude position? Because in this case, in the equilibrium position also velocity is 0.
Okay. It was 0. Now think of it like this. Forget the equilibrium position for a while. This will remain the equilibrium position. But now when I bring it down by 10 centimeters and let go the particle, when it comes to the equilibrium position, it would have developed a velocity because of the spring force acting upwards, isn't it?
Yes, sir.
So it will remain the equilibrium position and velocity will no longer be 0. See, next when it comes back to this position, it will have an upward velocity, say v naught, at the mean position, isn't it? It's not going to be 0.
Sir, if we remove the hand abruptly,
I'll do that now. Let me do that, please. But so far so good, right? Omega will be root k by m. Equilibrium position would be x naught equal to mg by k. Amplitude would depend on what we do to the particle.
So, if you said it will come up with the velocity v naught at the equilibrium position, then when it comes, if it is exhibiting SHM, so when it comes back, it has to
V naught downwards.
not downward.
Yes, of course. See, v at any x is given by omega root a squared minus x squared. No matter when and how it comes to that x, it will have the same speed. Isn't it? Clear? Please ask questions. So far so good, right? Now, let me be stepmotherly with the particle. Okay? हाँ, let's see ना, फिर यार थोड़ा सा पढ़ाने भी दे यार, देख लेते हैं होगा नहीं होगा, we'll know very shortly. Vertical spring once again, everything else remains the same. Mass m in its natural state, the spring in its natural state, this is x equal to 0. Ideal spring, force constant k. Abruptly withdraw support. जैसे कुशल करता है. Sorry, हाँ? कुशल, Huh? You're fine now. So I abruptly withdraw support from the mass M. Okay? Poor fellow. When we abruptly withdraw support from the mass M, it will come down, but not slowly, rapidly, because it will accelerate with a difference equal to mg minus the spring force. Initially, mg will be more than the spring force, so acceleration would be downwards. It would develop a velocity, right? It will develop a velocity. Instead of coming down very slowly, it will develop a velocity. Now, its equilibrium position, even though it develops a velocity, its equilibrium position will be the same. Because the amount by which the spring has to elongate, x naught, must be, in order to balance mg, must still be the same, isn't it? So, equilibrium position, kx naught, must be equal to mg. The only difference is this time it has arrived at the equilibrium position with its own velocity. It didn't have a caretaker, so it developed its own velocity, right? Now, it will go down till this point, from x equal to 0 to x equal to x naught. Mg was bigger than spring force, so the particle accelerated, right? From this state to this state, spring force was only beginning to grow, whereas mg was the same. So mg was till a certain x naught, mg was bigger than kx naught. At mg equal to kx naught, there was equilibrium. By the time, even though there was equilibrium, it has developed a velocity, so it will go down further because of inertia. If it goes down further now, the spring force will exceed mg. So from this point onwards, it's going to retard, right? So it accelerates in this regime, whereas it retards in this regime. Therefore, this must be a state of maximum velocity. This must be a state of maximum velocity. You expect that to happen in equilibrium position, right? You would expect then, at the lowermost extreme, the velocity to become 0. And say, this happens at some x equal to x. This happens at some x equal to x, velocity becomes 0. Alright. Now, between this state A and this state B, can I apply work energy theorem? What's the work done by mg? mgx. Between A and B, we'll apply classical work energy theorem. So work done by gravity would be mg into x. What's the work done by the spring force? Minus half kx square. And this must be equal to change in kinetic energy, final minus initial, that is 0. So that gives me x equal to 2 mg by k, which is 2x naught. Now you had no control over its amplitude, which is 2x naught, isn't it? Isn't it? Therefore, this is the equilibrium position. X turns out to be 2x naught. Therefore, what would this be? This length will also be x naught. This is the main position. This is the lower extreme. This is the upper extreme. And the amplitude is x naught. This time, see, the particle didn't give you control over its amplitude either. It built its own amplitude because you didn't care for the particle, right? So it had its own amplitude, x naught, which is mg by k. Omega, of course, remains root k by m, irrespective of whether there was support or no support. Omega remains root k by m for each situation. Does that make sense to all of you? So you understand this dynamics of a vertical spring in both cases, where you move the particle very slowly down and withdraw support at the equilibrium position and then pull it and incite vibrations, or at the word, from the word go, you leave the particle unattended. Both cases you register properly, right? Now, So far so good, right? Suppose there was a spring, force constant K, okay, and was in equilibrium. There was a mass m1 and a detachable mass m2. And the two masses and the system was in equilibrium and at rest. In equilibrium and at rest. And at rest. Do you imagine that this will not be the natural state of the spring? The spring ought to exert an upward force to balance m1 m plus m2 into g. So the spring must have elongated by a certain amount. The spring must have elongated by a certain amount. This must have been the natural state of the spring. This must have been the natural state of the spring. And for producing equilibrium, the spring must have elongated by an amount x naught such that the spring force balances the weight downwards. The velocity of the combo is 0 in this state. The velocity of the combo is 0 in this state. Now, suddenly I remove the mass m2. So now the spring force will become more than the weight. Weight has decreased. The spring force, therefore, kx naught must be more than m1g. Therefore, the mass will move up. The mass moves up. And it moves to a new equilibrium position. There would be a new equilibrium position. For m1, realize that the equilibrium position must be, say this is x1, which is m1g by k. Do you realize this? In order that the mass m1 is in equilibrium, the spring must have had an elongation x1 such that kx1 is m1g. Yes or no? The equilibrium position of mass m1 must be commensurate with elongation of the spring x1 such that spring force kx1 balances m1g. Right? This is the equilibrium position for m1. This must be this length. See, this entire length x naught was m1 plus m2 g by k. Yes or no? The particle starts to have an upward velocity when m2 was withdrawn, right? And this was an extreme state. This was an extreme state. This is the equilibrium position. This is the separation between the extreme state and the equilibrium position. This therefore must be the amplitude of motion. This therefore must be the amplitude of motion. Therefore the amplitude, as you can see, this length must be m2g by k, isn't it? Because this whole is m1g by k plus m2g by k. This is m1g by k, so this must be m2g by k. So the amplitude of motion must be m2g by k. Look, Diptesh, there was the spring and a total mass m1 and m2, okay, and it was in equilibrium. That means the spring must have, this was the natural state of the spring must have elongated by an amount x naught such that x naught, kx naught is the weight, right? Now if I remove m2, the mass will move up because the spring force is in excess of the weight. There would be a new state for m1. There would be a new state for m1 in which the spring has got elongated by an amount x1 such that the spring force becomes equal to m1g. This will be the equilibrium state for m1 alone, which is this equilibrium state for m1 alone. For m1 this must have been an extreme state because this is zero velocity. This must have been an amplitude position, right? This was an equilibrium position. The separation between the two must have been the amplitude of motion, right? And this is m1g by k plus m2g by k. This is m1g by k. So this must be m2g by k. The amplitude must be m2g by k. Omega will remain the same. Root k by m1 would be the omega for the motion. Does not matter. Yes. If absolutely, if m2g is bigger than m1g by k, that means if m2 is bigger than m1, it will compress the spring.
So in that case, another force will not come into play, that kx naught which is exerted by the compressed spring?
No, I mean the spring will compress till such time the velocity becomes zero. That's all. It will still move up by an amount a, which is m2g by k. Spring force has always been there. Below this position, it has been elongation. Upward force. Above this position, it has been downward force. But that's not going to change things at all, right?
So, but the spring will get compressed anyway, even if m1 is less than m2.
If m1 equal to m2, the spring will not compress. If m1g is m2, if m1 equals m2, then this length will become equal to this length. So the spring will just about reach its natural state. This is the natural state of the spring. It will not get compressed. If m2g is bigger than m1g, that means if m2g by k is bigger than m1g by k, then it has the amount by which it has gone down is the amount by which it has to move up. And if m2 is bigger than m1, then m2g by k would be bigger than m1g by k, and it will overshoot the natural length of the spring. It will compress the spring. Is that okay? So if m1 equal to m2, the spring will never get compressed. If m2 is bigger than m1, spring will get compressed. If m2 is smaller than m1, the spring will always remain elongated. Is that okay or not okay? And omega will remain root k by m1. Initially, though, it was at rest, yaar. The whole thing, there was no omega at all. Omega happened only after I withdrew a mass and it was set into motion. Until then, it was quietly sitting sedate, doing nothing. Right? Is that okay? Now, suppose, see, you took away the mass m2, but it left its traces behind in the form of an amplitude which was m2g by k. So it was not like that the amplitude was independent of the mass that you withdrew. It left its representative m2g by k as the amplitude, right? That is what transpired. Now, suppose there was a mass m1 in equilibrium. In equilibrium. This is not the natural state of the spring. This is in equilibrium. This is the natural state of the spring. The mass m1, the spring has got elongated by an amount x1 such that kx1 is m1g. That is what brings it to this equilibrium position, isn't it? And it's sitting there at rest without nudging, doing nothing. Okay. Now there is a mass m2 that falls on top of this and hits this mass with a velocity u and stays on top. It just about hits this mass with the velocity u and it stays attached to f1. It would then have incited oscillations in the mass. The two masses then together will execute simple harmonic motion. The two masses then will execute simple harmonic motion. However, this for m1 and m2 together, this will no longer be the equilibrium position. That will get revised, right? However, oscillations will get incited in the combo m1 plus m2. Now, m1 plus m2 would acquire a new equilibrium state. So this will not be the equilibrium state anymore. This was the equilibrium state for m1 alone. But now for m1 plus m2, this would be the equilibrium position, say x naught is the equilibrium position. x1, so let me call it x2. x2 is the equilibrium position for m1 plus m2, right? In both cases, this original state of the spring and the state of the spring in the equilibrium position of m1 plus m2. The spring is elongated. The spring is all along elongated. I want to find the total energy of this oscillator. I want to find the total energy of oscillation. This is the equilibrium position means what must be kx2 equal to? Spring force kx2 must be m1 plus m2 into g, isn't it? This is the new equilibrium position. So k x2 is m1 plus m2 into g. The equilibrium position for this oscillator. What would be the omega of oscillation? Root k divided by m1 plus m2. This is the simplest thing to deal with, right? This is the new equilibrium position for the combo m1 plus m2, which is executing simple harmonic. I want to find the total energy of this oscillator. I want to find the total energy of this oscillator. Do you realize the total energy of oscillation is the kinetic energy at the mean position? Isn't it? Total energy of oscillation would be kinetic energy at the mean position, isn't it? Or potential energy at the extreme positions. So if I can find kinetic energy at the mean position, that will be the total energy of oscillation. That will be the total energy of oscillation. Kinetic energy at the mean position would be the total energy of the oscillator, right? Say by the time the oscillator attains its equilibrium position, its velocity becomes v naught. Its velocity becomes v naught. Okay? Now between state A and state B, I'll apply work energy theorem. Let me apply work energy theorem between state A and state B. Forces acting. When the particle goes from state A to state B, only two forces acting on the particle, mg and spring force. Isn't it? What's the work done by mg? m1 plus m2 into gx2 is the work done by gravity, right? What's the work done by the spring force? Negative of the change in elastic potential energy, minus half k x2 squared minus x1 squared, and x2 squared minus x1 squared is the change in elastic potential energy of the spring. Yes or no? In this state, what's the elastic potential energy of the spring? Half k x1 squared. What's the elastic potential energy of the spring in this state? I'm sorry, this is x2 minus x1. x2 minus x1. It has gone from this point to this point. It has gone from this point to this point. So the work done by gravity would be m1 plus m2 g. This, why yaar? This is the equilibrium position. This was the original state. This is the natural length of the spring. Why are you assuming that this would be an extreme state or this would be the mean position? Please, I think I've got you held for very long. Let me cool you down with stuff. देखो ये मास m1 जो था यहाँ शांति से बैठा हुआ था, इक्विलिब्रियम में था. स्प्रिंग इस केस में इलोंगेटेड था ससुरा. कितना इलोंगेटेड था? It was elongated by an amount x1 such that kx1 was just balancing m1g. यहाँ तक ठीक है? This was not the natural state of the spring. The natural state of the spring was this, right? This fellow comes, bangs on this mass m1. The mass then moves down. Together then m1 plus m2 acquire a new equilibrium position where m1 plus m2g is balanced by the new spring force when the spring has got elongated by an amount x2 from the natural state, right? So the particle has gone, okay, this, you're saying this is A and B. Okay, what was that? This A and B. So this is a state A and this is state B. So m1 plus m2g into this length is the work done by gravity. This length is x2 minus x1. Work done by the spring force, negative of the change in elastic potential energy, half k x1 squared, half k x2 squared. So that's this. And that must be change in kinetic energy. That means kinetic energy at the equilibrium position minus the kinetic energy here. What's the kinetic energy here? No. There she goes. See, when the two strike, then m2u is the momentum that this brings to the system. Together, m1 and m2 move with a velocity v0. Conservation of linear momentum this way, yes or no? See, this was m1, m2 was at rest, or rather this was m2, this was m1 at rest. m2 was moving down with a velocity u, right? Just before collision, just after collision, this is m1 plus m2. Together they move down with a velocity v0. Then conserving linear momentum in this direction, m2u equals m1 plus m2 v0. Yes or no? That's the total linear momentum that this is bringing. This has zero linear momentum, this has m2u. Final linear momentum is m1 plus m2 into v0. Now, why could I not do this? Tell me. Why not did I not say half m2 u squared equals half m1 plus m2 v0 squared? Why did I not say this? Huh? Correct, na? अबे ससुरा सब मास है यहाँ पे. Now tell me, why did I not do this? Why did I conserve linear momentum and not conserve energy? Who said that? Who said that? Yes, 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 absolutely. See, if this guy strikes this and they stay together after collision, the collision is perfectly inelastic. Kinetic energy is not conserved in a perfectly inelastic collision. Do you realize this collision between m1 and m2 is perfectly inelastic? Relative velocity of separation is zero. So kinetic energy is not conserved, but momentum always is. Therefore, this is wrong. Shashi bhai. Right? This is not right. It's a perfectly inelastic collision. Kinetic energy is not conserved, but linear momentum is. So I know V naught. I know V naught. So kinetic energy, the equilibrium position will be the total energy of the system minus kinetic energy at A. Minus kinetic energy at A. What's kinetic energy at A of the system when it starts to oscillate? half m1 plus m2 into v naught squared would be the kinetic energy at A. Yes or no? Bolo? Got me? This v naught I know, I can transpose on this side. x1 and x2 also I know from those conditions. Therefore, I can know, I can find out, I can calculate the kinetic energy at the equilibrium position, which would be the total energy of the system, which will be the total energy of oscillation. That's going to be the total energy of oscillation. The kinetic energy at the equilibrium position will represent the total energy of oscillation. Confused kya? Right? Simple. Hey, just in case you know, this was not V naught, this was V naught prime. V naught was the combined velocity of m1 and m2 right after the impact. So just to distinguish between, I never even used this V naught. The V naught that I have used in this equation is the combined velocity of m1 and m2 right after impact. So just stand corrected. Now, simple, right? Shall we proceed then? Now, there is a platform and it's executing vertical oscillations of amplitude A and angular frequency omega. By some means, it's executing vertical oscillations of amplitude A and angular frequency omega. By some means. There is a particle of mass m. There is a particle of mass m sitting on the platform and executing the same simple harmonic motion, amplitude A and angular frequency omega. Between these two limits, say A units above this, and it could go A units below this. This is the equilibrium position, the one that you see here. Right? A units above this, A units below this. Now, let me imagine the platform to be at some instant of time x naught units below the equilibrium position. Let me imagine at some instant of time the platform to be x naught units below the equilibrium position, right? Now, let me look at the free body diagram of M, the particle M. What are the forces that act on M? mg downwards, normal reaction upwards, right? In order that M executes simple harmonic motion, the net force acting on this towards the equilibrium position must be proportional to x naught. Must be some k times x naught. Let's say k is the force constant, isn't it? So the net force acting on this towards the equilibrium position is n minus mg, and that must be some k times x naught. The magnitude of the force towards the equilibrium position must be proportional to the displacement from the equilibrium position, right? Where omega squared is k by m, So k could have been written as m omega squared. K could have been written as m omega squared. Omega is the angular frequency for oscillation. So this gives me like a n minus mg is m omega squared x naught, where x naught units below the equilibrium position is where the platform is, right? N therefore must be m into g plus omega squared x naught. Yes or no? This is below the equilibrium position, below the EP, right? Which means no matter what omega I assign, no matter how much x naught goes, what is the maximum value of x naught? A. Maximum x naught could go 2a, 3a, 100a. N will never become 0 below the mean position. N will never become 0 below the mean position. Yes or no? In a vertical oscillation of the platform, the normal reaction acting on M will never become 0 below the mean position. So below the mean position, this particle has no threat of losing contact with the platform. What defines the state of loss of contact with the platform? N becoming 0. When N just about becomes 0, it defines the state of loss of contact with the platform, right? But N is never becoming 0. Since N is never becoming 0 below the platform, all states below the platform, irrespective of omega and A, will be safe positions for M. Because N is not becoming 0, the particle is not vulnerable towards loss of contact, right? So below the mean position, N never becomes 0, no loss of contact ever takes place. Of small m with the platform. Right? Whether you increase omega, decrease omega, increase amplitude, decrease amplitude, for no value of x naught below the mean position, there would ever be loss of contact, right? Now, let me examine x naught units above the mean position. Let me examine x naught units above the mean position, right? Confused, kya? Do you understand this equation? Can n ever become 0 below the mean position? So if n is not becoming 0 below the mean position, contact will never be lost. Contact of small m will be lost with the platform if n becomes 0, isn't it? Hurry, that's what I taught in Newton's laws all along. Loss of contact is about n becoming 0. Isn't it? Did I ever tell you that contact is about n not being 0? Right? So below the mean position, it's doing good. Okay. Now let me examine the particle, the platform above the mean position. Say x naught units above the mean position. Right? The platform is x naught units above the mean position. Again, the forces acting on it are n like this, mg like this. What's the net force towards the mean position? Mg minus n. So now above the mean position, mg minus n must be some k times x naught. The net force must be proportional to displacement from the mean position and directed towards the mean position for it to execute SHM, right? This, of course, k like before could be written as m omega squared. K could have been written as m omega squared. So n then becomes m into g minus omega squared x naught. Positions above the mean position are sensitive towards loss of contact because here n could become 0. If g becomes equal to omega squared x naught, that means isn't it? Then there could be loss of contact. That means when the particle is executing simple harmonic motion and at certain times it's above the mean position, then it could lose contact. It could lose contact because n could become 0 above the mean position, right? N could become 0 above the mean position. Therefore, you must be careful about what the particle is doing above the mean position, how far it's going, what's the amplitude, what's the omega. That has to be investigated in light of stability of the particle on the platform or sticking on the platform at all times. While below the mean position, you can close your eyes. While above the mean position, for it to not lose contact, to maintain contact above the mean position, n must be greater than or equal to 0 to maintain contact, right? That means g must be greater than or equal to omega squared x naught, right? The platform renders unconditional support below the mean position, but above the mean position it says, hey, if the particle has to maintain contact, make sure that g is greater than or equal to omega squared x naught. That means x naught has to be less than or equal to g by omega squared. That's a limiting case. That's what we write. That's the maximum possible value. That means we are just smaller than that. That's all that it means. That's a limiting value of x naught. That means all that it makes sure is that this does not exceed this. This could be just slightly less than g by omega squared. Limiting case we include here. Limiting case we include here. So maximum x naught is root g by omega squared. That's all. Now, if the amplitude itself is less than g by omega squared, then x naught will be less than g by omega squared, isn't it? What's the maximum x naught? Amplitude. If the amplitude itself is less than g by omega squared, then x naught will be less than g by omega squared. So it suffices to say that a should not exceed g by omega squared. A should not exceed g by omega squared. So if a does not exceed g by omega squared, x naught will never exceed g by omega squared, right? Which means, huh? Huh? Which one? This? Yeah. That's true. Now, no, that's for maintaining contact. That's for maintaining contact. So therefore, if you decide that this platform will execute SHM with a certain omega, and you have no handle over omega, right? Then you want to make sure that the amplitude of oscillation does not exceed g by omega squared. Or if you think that, well, this platform has to go to this position to perform a certain action. That means if you want to maintain the A, then you want to make sure that the omega of the platform does not exceed, omega squared does not exceed g by A. See, there are two things you could play around with. You could play around with A, fix omega, and make sure that the amplitude does not exceed g by omega squared, then that's good enough. Or the second thing you want to do is the physical situation demands that the amplitude is A. But then let's say by some mechanism you could vary omega for the system, right? Then you want to make sure that omega does not exceed root g by A. So there is a maximum omega or there is a maximum A within which you will have to work for the particle to maintain contact at all times. So this is the story of the vertical platform. This is the story of the vertical platform. You understand this? And you must remember this result. The omega not exceeding root g by A or amplitude not exceeding g by omega squared for maintaining contact. Clear? See, till this point, the way we've dealt with oscillations was, we said force proportional as minus kx or minus kx plus c, writing force equations directly. Now, what we'll do is, we'll use energy methods to obtain the omega or the force constant for oscillations. In the sense, this is what I mean really. See, the moment I have f equal to minus kx plus c, I can conclude that the motion is simple harmonic with omega being root k by m. Or if I had acceleration, which is v dv dx, do you realize acceleration is v dv dx? Right? As minus omega squared x plus some constant, then the motion is simple harmonic with angular frequency being omega. Right? Now, when I talk of energy methods, say for a regular oscillator, force constant K, natural state of the spring, equilibrium or the natural state of the spring, at a certain instant, let's say, at a certain instant, the mass was displaced by an amount x, and let's say had a velocity v. The mass was displaced by an amount x and had a velocity v, right? Now, what was the total energy of the system? Half kx squared plus half mv squared was the energy of the system in this state. And the energy of the system will remain the same in all states, will be the same for all values of x, right? E will be the same for all x, independent of x. E therefore will be independent of x, yes or no? Same for all x means independent of x, that's what it means, yes or no? Yes. That means if E does not depend on x, then dE dx must be 0. If E does not depend on x, then dE dx must be 0, yes or no? Okay. So now, half kx squared plus half mv squared. So let me put dE dx as 0. Let me put dE dx as 0. So once I put dE dx as 0, then I get kx plus mv dv dx as 0. Yes or no? Kx plus mv dv dx. If I differentiate v squared with respect to x, I get 2v dv dx. Yes. I'm assuming you've not forgotten your differentiation, right? Okay, so that gives me v dv dx as minus k by m into x, where minus k by m could be looked upon as omega squared. Therefore, the motion is simple harmonic with omega being root k by m. With omega being root k by m. Yes or no? Suppose I had a vertical spring, force constant K, right? And say this was the natural state of the spring. This was some position of natural state of the spring, and the particle was executing SHM, and this was x equal to 0, right? After a while, the particle descended by an amount x and acquired a velocity v. Okay, let me write the total energy expression at x. Let me write the total energy expression at x. Let me call this as 0 of gravitational potential energy. If this is 0 of gravitational potential energy, then anything below this will be negative potential energy. So then the gravitational potential energy here would be minus mgx, yes or no? Isn't it? If the gravitational potential energy was 0 here, then x units below this, it will be minus mgx, right? Now the total energy for the system. At this x, the total energy of the system would be minus mgx plus half mv squared, right, plus half kx squared. That's the total energy of the system at x. Yes, please ask. Minus mgx, why minus mgx? See, if I go x units above this, potential energy will be mgx. If I go x units below the earth, the potential energy will be minus mgx. Right? Isn't it? So I can choose anything as the zero of potential energy. See, this point x units will be potential energy mgx higher than this point, and this point in potential energy will be mgx lower than the potential energy of this.
Vertical, that's why it's that minus mgx potential also.
Yes, 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 yes. Are you all there with me, or am I confusing you? No, no? See, I don't want to damp you because I have still not done damped simple harmonic motion. All right, so stay upbeat. We'll do that. Hey, Ishan has become a good boy, sitting in the front last 2 classes. Very good. No, that's not right. So E again, total energy of the system must be independent of x, isn't it? I want to first figure out if the motion is simple harmonic, right? So I say, well, there are no dissipating forces here, so the total energy of the system must be constant. So dE dx must be 0. E must be independent of x. So dE dx is equal to 0. Right? Or I get minus mg plus mv dv dx plus kx as 0. Elastic potential energy of the spring, half kx squared. If the spring is elongated by an amount x, then its potential energy would be half kx squared. If it's also compressed by x, then also it's going to be half kx squared. When did I write minus half kx squared? No. Huh? No, this is not work done. This is potential energy of the spring. This is the potential energy of the spring. This is not the work done by the spring. Is that okay? So this gives me v dv dx, the acceleration, as minus k by m into x plus g. Yes or no? Therefore, acceleration is minus omega squared x plus a constant. Motion must be simple harmonic. Omega of the oscillator therefore must be root k by m. Hey, the equilibrium position would be one where a becomes 0. This is the acceleration. V dv dx is the acceleration. And when a becomes 0, you get the equilibrium position. X will be mg by k, will be the equilibrium position. This will be the equilibrium position. Where a becomes 0 will give you the equilibrium position. Yes or no? Confused? No? E is the energy at x, but the total energy should not depend on x. It will be the same for all values of x. So its rate of change with x must be 0, isn't it? If E does not depend on x, and now you differentiate E with respect to x, will it not be 0? Right now? Now, on similar lines, look at the circuit. हाँ 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 राइट राइट छोड़ दिए थे उसको, वही किए. Right? Now look at this circuit. Let me explain the circuit to you. अरे बिस्कुट नहीं बोला, चिरकुट बोला. कौन बिस्कुट बिस्कुट बोलते? बिस्कुट. All right, check this out then. So there is a fixed pulley and a force constant K. This is a spring all along. It's not that it's partly a spring and partly a string. The whole thing is a spring. Force constant K, mass M. Right? And say this entire thing is a spring, by the way. Right? I want to find what m does. I want to find what m does when released from this position. This is, say, x equal to 0. This is x equal to 0, the natural state of the spring. Say this is the natural state of the spring, right? When you withdraw support from m, m will descend, it will develop velocity, the spring will elongate, right? So, after a while, the mass m descends by an amount x and develops a velocity v. Clear? Let me write the total energy expression for the system. The total energy expression for the system would be, okay, potential energy minus mgx, gravitational potential energy, elastic potential energy of the spring, half kx squared. The spring has got elongated by an amount x. This entire thing is the spring. So if the mass moves down by an amount x, the spring must have got elongated by an amount x, right? So half kx squared is the elastic potential energy of the spring and the kinetic energy of the mass. That's the total energy of the system, which is not changing with x. It's going to be the same for all x. So rate of change of E with respect to x must be 0, isn't it? Or minus mg plus kx plus mv dv dx. V dv dx is the acceleration. This must be 0. Or we get v dv dx as minus k by m into x plus g. So we have like acceleration equal to some minus omega squared x plus g. This must be simple harmonic, where omega squared must be k by m and the omega for the oscillator must be root k by m. So this mass executes simple harmonic motion with angular frequency root k by m. Clear now? Right? Let me illustrate a little more. Pura spring. See, otherwise this entire thing is a spring, you know, this whole thing has to elongate, right?
अगर partly spring और बाद बाकी spring हो तो भी वो spring जैसी काम करेगी.
You're right. There is a spring of force constant K attached to a pulley like this, and now there is a string. This is a string and a mass m attached here. All right. We want to find out what the mass m does. What the mass m does. Let's say initially the spring is in its natural state. This is the spring and it's in its natural state. Okay. Now, one thing, this was the pulley, right? If the pulley moves down by an amount, say x naught, then see, moving this pulley down, this was the original position of the pulley, this was the original position of the pulley, right? When the pulley is moved down, this x naught and this x naught will become free, and this part will wound around this, and this x naught will result in descent of the mass m by an amount 2x naught. Yes or no? Yes, sir. That means if the mass m descends by 1 centimeter, the spring must have got elongated by half a centimeter. Yes or no?
Yes, sir.
Right? So which means, let's say this is x equal to 0 for the mass, unstretched state of the spring, the mass descends, say, by an amount x, right? So the pulley will elongate by an amount x by 2. Yes or no? Yes, and let's say in this state, the mass develops a velocity v. By the time it descends by an amount x, it develops a velocity v. Now, let this be the zero of gravitational potential energy. Then what would be the gravitational potential energy here? Minus mgx. So what would be the total energy at x? Minus mgx plus half mv squared plus half k x by 2 whole square. Yes or no? d dx will still be 0. d dx will still be 0. Minus mg plus mv dv dx plus 1/4 k x must be 0. Yes or no? No? So this gives me v dv dx as minus k by 4m x plus g. So we again have a equal to minus omega squared x plus g. Motion must be simple harmonic with omega squared being k by 4m. Omega squared being k by 4m. So the angular frequency of oscillation of this would be root k by 4m. What would be the time period? Time period would be 2 pi by omega. Yes, I'll explain. Did you understand this? This part? Then the same thing. If the spring elongates by an amount x naught, the mass descends by 2x naught. That means the spring is elongating by exactly half the amount the mass is descending. Isn't it? Did you understand this? That's exactly what I did. The spring elongates by an amount half the displacement of the mass downwards. So if the mass has gone down by an amount x, the spring must have elongated by an amount x by 2. Isn't it? Or shall I explain this part? No? Clear now?
Sir, but this is the energy of the whole system together.
Yeah, but this will give me the acceleration of m, isn't it? And the energy of the entire system will remain the same. There are no dissipating forces, right? So this is the acceleration of the mass. So I'm talking of the oscillation of mass m. And what would be the mean position of the mass m? The value of x for which this becomes 0. That means x equal to 4 mg by k would be the equilibrium position of the mass m. Isn't it?
So what will be the equilibrium position?
One for which a becomes 0. See, this will become 0 at x equal to 4 mg by k. That's the equilibrium position, isn't it? Is that okay? Okay, let's illustrate a little more. This entire thing is a spring. Mass m attached here. Okay, spring of force constant k. Look, if the pulley descends by a certain amount, say the pulley has descended by an amount x. The pulley has descended by an amount x. Then do you realize that the spring length on either side has increased by an amount x? See, this is the spring. This is the spring. If the pulley descends by an amount x, then the spring length on this side has increased by an amount x, on this side it has increased by an amount x. That means spring has increased by an amount 2x. Perfect. Right. So if the mass m descends by an amount x, that means the spring must have moved down by an amount. The pulley must have moved down by an amount x, and the spring must have elongated by an amount 2x. So spring elongates by an amount 2x. Can explain again? I'm saying, see, this was the original pulley. When you pull the pulley down by an amount x, then this part of the spring increases by an amount x. This part of the spring also increases by an amount x, isn't it? Because this would be the new state of the spring, right? So the total spring length increases by an amount 2x when the pulley has moved down by an amount x. And the amount by which the pulley moves down is the amount by which the mass moves down. So if the mass has moved down by an amount x, the pulley moves down by an amount x. On either side of this pulley, the spring elongates by an amount x. Therefore, the total elongation in the spring will be 2x. Right? So, the spring elongates by an amount 2x. Say this is x equal to 0. By the time the mass has moved down by an amount x, let's say the velocity is v. The total energy at x, let me write the expression for the total energy at x, right? The total energy at x is going to be minus mgx, gravitational potential energy, half mv squared plus half k into 2x whole squared. Yes or no? So instead of k, we have 4k now. See, it's the same as the earlier one. Instead of k, we have 4k. So if I differentiate this with respect to x and put equal to 0, then I must end up getting omega same as what it was, except that k becomes 4k. Bless you. Omega becomes 4k by m. Isn't it? I hope you realize this. Instead of k, you have 4k now. This is what would happen. This is just a string, and this one is a spring of force constant k. Okay. Check this out, please. Say the pulley, position of the pulleys is given by, say, x. Okay, and this is given by an amount, say, x naught, the center of this pulley. The centers of these two pulleys given by x, the center of this pulley given by x naught. Okay. No matter what, the total string length must be constant, right? This length is x. This is also x. So this plus this is how much? 2x string length plus this is x, this is x naught. So this is x minus x naught plus x minus x naught. That makes it twice x minus x naught. Total string length, which is twice 2x minus x naught. Right? Now, delta L, L is the string length, delta L will be 0, isn't it? Delta L will be 0. But delta L, change in L is twice delta in x minus delta of change in x naught. Yes or no? Change in L will be 2 times twice change in x minus change in x naught. And this must be 0. Right? That means delta x naught must be twice delta x. Yes or no? That means if these two pulleys move down by 2 centimeters, then the spring must elongate by 4 centimeters. Yes. Block moving down by an amount x would mean this spring will move down by an amount twice x. I can repeat this if you have not understood. If the mass, yes, I'll explain. Did you understand this part? Pakka? What it really means is, the way to read this is, the amount by which the spring has got elongated, delta x naught means change in x naught, means the amount by which the spring has got elongated, isn't it? Delta x naught means change in x naught. Change in x naught means what? Change in the length of the spring, means the elongation in the spring is delta x naught, is twice delta x. Change in x. Change in x is the amount by which the mass has moved down, isn't it? So the amount by which the spring has got elongated is twice the amount by which this pulley has moved down. Delta x is what? Change in x now. Change in x means the amount by which the pulley has moved down. So the change in spring length will be twice the amount by which these pulleys would have moved down. So if these pulleys have moved down by 1 centimeter, the spring will elongate by 2 centimeters. If the mass has moved down by 1 centimeter, these pulleys will move down by 1 centimeter and the spring will elongate by 2 centimeters. I can explain again if you have not understood. Pakka? All of you have registered this? Right? So, once we have this fact in our kitty, then it's as simple as this. Forget all of this now. Say the mass at a certain instant from this position, which is the natural, this represents the natural state of the spring. While the mass is here, the spring is in its natural state. Okay? And after a while, the mass descends by an amount x and develops a velocity v. The mass descends by an amount x and develops a velocity v. Okay. By what amount will the spring elongate? 2x. So the spring will elongate by an amount 2x. That's what it means. Let me write the energy expression. Let me look upon this as the zero of gravitational potential energy. Then this would be minus mgx. This would be minus mgx. So the total energy E would be minus mgx plus half mv squared plus half mv squared plus half k into 2x whole square, and dE dx equal to 0. You don't have to reinvent the wheel. See, instead of k it becomes 4k, so 4k by m would be omega squared, right? So omega squared would be 4k by m, omega would be root 4k by m, time period of oscillation would be 2 pi by omega. Makes sense to all of you? Huh?
So, while considering this energy, we take the velocity of the block, but the velocity of the pulley.
Pulleys are light. If the pulleys had mass, we would take their kinetic energy. If we are talking of ideal pulleys, we are talking of light pulleys. See, there could be a non-ideal spring. The spring could also have mass. Then they will also have to take the kinetic energy of the spring. Right? So in this case we are assuming ideal spring, mass lightless, ideal light frictionless pulleys. So there, otherwise I would have to write the kinetic energy of the pulleys also. Right? I would have had to do that. So far, so good.
Yes, sir.
Uh, what I'll expect you to do is please attempt 5 and 6 right now. 5, 6, 7. Please attempt 5, 6, 7 right now. All right. Let's look at 5 then. Let's look at 5. All right. There are two springs of force constant K1, K2 joined somewhere, does not matter where they are joined. Mass M. Okay. Let's say when the mass M descends by an amount x, when the mass M descends by an amount x, say this spring of force constant K1 elongates by an amount x1 and spring of force constant K2 elongates by an amount x2, say. Right? We do not know x1 and x2. When this mass M descends by an amount x, both these springs will elongate. Say spring 1 elongates by an amount x1, spring 2 elongates by an amount x2. Right? Now, how is this x1 and x2 related to x? That's the next question. Right? Yes. See, very good. This total elongation is x1 plus x2. The total elongation of this is x1 plus x2, where this part doesn't change in length. This part doesn't change in length. Only this and this will change in length, isn't it? Right? Which means, if you look at this movable pulley, this part and this part. This part and this part together will increase by an amount x1 plus x2, right? So then if the pulley moves down by a certain amount x, that means the mass has moved down by an amount x. If the pulley has moved down by an amount x, then realize that this portion of the spring will increase by an amount x, and this portion of the spring will also increase by an amount x. So the total change in length of the spring is going to be 2x, which must be x1 plus x2. Yes or no?
Yes.
Right now? 2x must be elongation of spring 1 plus elongation of spring 2. Right? However, this is one single spring. So the tension must be the same at every point of the composite spring. Tension in this spring is K1 x1 because it has elongated by an amount x. Tension in this spring is K2 x2, and the two must be the same. Because it's one single spring, it must be the same tension everywhere. Therefore, we must have K1 x1 equals K2 x2, where 2x is x1 plus x2. Right? Can I not solve for x1 and x2 from this equation? I can solve for x1 and x2 in terms of x. So I would know x1 in terms of x. I would know x2 in terms of x. Right? Yes or no? Now I'm ready to write the energy equation. I'm ready to write the energy equation. That means if this mass has descended by an amount x, say it develops a velocity v. Okay? So if it develops a velocity v, then the total energy of the system is going to be what? First of all, minus mgx plus half mv squared plus half k1 x1 squared plus k2 x2 squared, where x1 and x2 all I can write in terms of x. So again I do a dE dx equal to 0, right, and I would end up getting v dv dx as minus of something into x plus something is what I'll get. If I do that, this is what I'll get, right, where this thing then would be omega squared. This would be omega squared. This is what we need to do here. Confused? No? You'll be able to do it from this point onwards, right? Hmm?
Replaced by one spring.
You have to explain that properly then. In a certain sense, spring force is the same, but again, whether it's applicable to this situation or not has to be then explained. Explain it to me. Whether I can replace this combo by k1 k2 by k1 plus k2. Yes. Force in one spring will be equal to force in the other spring. This is one single unit. T must be the same at every point of this unit, right? Okay. You could, what you would have to then do is, you know, the total elongation here would be 2x and k could be replaced by k1 k2 by k1 plus p2. That's how you could do it. Yes. Okay. Again, the two springs initially, their natural length. So I could look upon this spring as k and this one another k and so on and so forth. Didn't really make a difference. So if this mass m descends by an amount x, if this mass m descends by an amount x, right? Realize that this part of the spring will increase by an amount x, this part of the spring will increase by an amount x. So this spring will increase by an amount 2x, this spring will also increase by an amount 2x. Yes or no? Right? Now the energy expression, say by the time the mass descends by an amount x, it's developed a velocity v. So what's my energy expression? Minus mgx, right, plus half mv squared plus 2 springs half k into 2x whole square. That's the energy expression. All that you need to do is dE dx equal to 0. See, actually what you end up getting is, instead of k you have 8k. 8k is what you will get. If you differentiate that, you will get root 8k by m. Right? See, this is 4k into 2, 8k, half of 8k x squared. Half of 8k x squared. So you will end up getting root 8k by m as the omega of oscillation. Time period would be 2 pi by omega. Sorry? So, see, essentially, what would then be the total elongation? Do you really think? Naina? Okay.
So, because of one spring, people apply parallel resistors.
You could do that. Parallel, then one single spring. What parallel then you have? If it's one single, then what parallel? K2. Say this mass m descends by an amount x, right? And say this spring elongates by an amount x1 and this spring elongates by an amount x2. Okay? Let's look at a relationship connecting x1, x2 and x. Think of it like this. For a moment, imagine that this was just a string. This didn't elongate. And this elongated by an amount x2. For a moment, just imagine that. That means if this pulley descends by an amount x2, see, if this pulley descends by an amount x2, if this pulley has descended by an amount x2, this part of the string will be released, this part of the string will be released, and it will result in a descent of this mass by an amount 2x2. Yes or no? See, if this pulley descends by an amount x2, please notice that. If this pulley descends by an amount x2, this would be the free length of the string, x2 units. This will be the free length of the string, x2 units, and it will result in descent of the mass 2x2. Yes or no? That means elongation of this spring by an amount x2 must have independently caused this mass m to descend by an amount 2x2. Right? No? Vertical, horizontal. Right? If this spring elongates by an amount x1, the mass will descend by an amount x1. If this spring elongates by an amount x1, this mass will descend by an amount x1. Therefore, the total descent of the mass m as a constituent of this and this would be what? X would be 2x2 because of this and x1 because of this. Yes or no? Can I say this? I still need to know one more condition so that I can solve for x1 and x2 in terms of the descent of the mass m. Right? We need to figure that out. Look at the free body diagram of this pulley. This pulley. There is a K2 x2 upwards. This spring is elongated by an amount x2. So there is going to be a K2 x2 upwards. And at these ends, there would be K1 x1 and K1 x1. Right? Light pulley, net acceleration, net force, K2 x2 minus K1 x1 minus K1 x1 must be mass of the pulley into acceleration. Mass of the pulley is practically 0. Right? So can I not say K2 x2 must be 2 K1 x1? No. अरे दोनों साइड ही तो स्प्रिंग हुआ है यार. ठीक है. स्ट्रिंग होने से भी वो टेंशन हियर वुड बी द सेम एज द फोर्स हियर. K1 x1 ही होता, सेम होता सब जगह. ठीक है, स्ट्रिंग होता तो भी. This one? Why? It'll always pull. Huh? For the force that the spring exerts on the pulley. This is the force that the spring exerts on the pulley, not on the mass M. See, this is the free body diagram of the pulley, not the free body diagram of the mass M. So it's like a string under a tension K1 x1, K1 x1. So that TT will act downwards on the pulley, na? That is all that I want to say.
Can't we do it directly, like suppose for example the pulley descends by 2x by x, then the pulley descends by x, so the block would descend by 2x and the K1 spring would elongate by.
Of course not. The two are independently acting. Why? The sum total of the change brought about by this plus this must be the descent of this. If this did not change in length and it descended by an amount x, then this would descend by an amount x by 2. If this did not change in length, but this is changing in length. So the net descent of this is not just because of the change in length of the spring, but change in length of this spring as well. That's a combined effect, right?
So x is 2x2, not 2x2 plus x1.
2x2 plus x1. See, if this elongates by an amount x2, it would have left x2 and x2 units free on this side, causing m to descend by 2x2, right? Plus, this now further elongates by an amount x1, causing the mass to m descend by an amount x1. So the net descent of the mass m would be x1 plus 2x2. The contribution made by this would be x1, the contribution made by this would be 2x2. Right now? So can I also say K2 x2 must be 2 K1 x1? Right? So I can solve for x1 and x2 in terms of x. Right? And then the total energy expression would be what? If this moves down by an amount x and it gathers a velocity v, energy would be minus mgx plus half mv squared plus half K1 x1 squared plus half K2 x2 squared. When you differentiate this, dE dx must be 0, which would give you A equal to minus of something into x plus something. Then this something would be omega squared. This something would be the omega of oscillation. Let me now teach you something very important, which is two body oscillations. Two body oscillations. Let me teach you at least this. After this, if you are tired, I'll just teach you one more thing and let you go. So we're talking of the following. Two masses, m1 and m2, connected by a spring. Of force constant K. Right? Let's say the two masses are initially at rest. Therefore, their center of mass would have zero velocity, right? If the two constituents are at zero velocity, so the center of mass will have zero velocity initially, right? And the spring is in its natural state. The spring is in its natural state. So then, this end of the spring and this end of the spring, which are connected to the two masses, these two ends, let me say small a, small b, represent the state of no force acting on M1 and M2, because the spring is not stretched or compressed. Therefore, no spring force, no force acting on M1 and M2 because of the spring. Clear? Now, very slowly. So essentially this was an equilibrium position for M1, this was an equilibrium position for M2. Let me call it EP1, let me call this EP2. Right? Now, and we'll assume that this surface is smooth and horizontal. Okay? Very slowly, I begin to compress the spring. I let the two masses come in closer together very, very slowly. I maintain the masses at zero velocity, that slowly. Alright. So, slowly the two masses are brought together. Right? Spring compressed very slowly by an amount x. X naught. Call it x naught. Spring compressed by an amount x naught. And since the whole operation is carried out very slowly, the two masses don't develop a velocity. The two masses don't develop a velocity. That means essentially the masses stay at rest. That means their center of mass stays at rest all the time. That means if this was the center of mass of the two masses initially, the center of mass never developed any velocity while the two masses were brought together, because the two masses never had a velocity, so the center of mass was never allowed to develop a velocity. So if the center of mass never developed a velocity, the position of the center of mass did not change with time. So even though I brought the two masses closer together, compressing the spring, it was not instrumental in producing any change in position of center of mass. Is that registered? Okay. Now, say M1 was brought to this position. M1 was brought to this position. M2 was brought to this position. In our attempt to compress the spring by an amount x naught, M1 was brought from this state to this state. M2 was brought from this state to this state. Right? And all of this did not result in any change of position of center of mass. Say M1 was compressed by an amount A1, say, and M2 was compressed by an amount A2. Therefore, A1 plus A2 is the total compression in the spring, which was x naught. A1 plus A2 must have been x naught, the total compression in the spring. Now, realize that to preserve the position of the center of mass, should I not have M1 A1, which is the disturbance brought about by this in the summation MIXI, should that not balance M2 and A2 so that the x coordinate of the center of mass did not change? Yes, sir. Right? Isn't it? Yes. So M1 A1 must have been equal to M2 A2 so that the x coordinate of the center of mass did not change with time. Right? So from these two, I can solve for A1 and A2. I can solve for A1 and A2. Yes or no? Don't start solving. Now, when I bring them to the state where the two masses have zero velocity, velocity of this is 0, velocity of this is also 0. The two masses have zero velocity in the state, right? Now I release the two masses. Now I release the two masses. Okay. So, in state C and D, in states C and D, the masses are released. Are released from rest. Right? So then this spring will push this mass m2 this way, this mass m2 will develop a velocity. This spring will push this mass m1 this way, this mass m1 will develop a velocity, right? So now from this state onwards, the two masses begin to develop velocity. m2 starts to move to the right, m1 starts to move to the left under the influence of the compressed spring. Okay? Now, while the spring begins to unfold, are there any external forces acting on the system comprising m1, m2 and the spring? No, there are no external forces acting on the spring mass system. And when the two masses were in state C and D, the velocity of the center of mass was 0. And there was no external force acting on the system. Therefore, the acceleration of the center of mass was 0, because there was any external force would have accelerated the center of mass. An absence of an external force would cause the acceleration of the center of mass to be 0. That means the x coordinate of the center of mass, since this really means that VCM remains 0, since there was, right? And if VCM remains 0, this would mean that the x coordinate of the center of mass remains constant. Right? That means the center of mass stays in this position all the time. While the spring unfolds, pushes masses m1 and m2 hit and the position of the center of mass does not change. The position of the center of mass does not change with time. Is that all right or not all right? Make sure you understand these ideas right now, right here. Okay? Simple, very simple. Now, after a while, m1 will come to this position, right? Where should m2 be? If m1 comes to state A, where should m2 be? It should be in state B. Why? Because it has to maintain the same position of the center of mass. So if m1 comes to this state and m2 was not in this state and at some other state, then the center of mass will not be this, would have got shifted. So which means both m1 and m2 come to the natural length of the spring at the same instant, come to their natural states at A and B at the same instant. Together they arrive at their respective equilibrium positions. Together they arrive at their respective equilibrium positions to maintain the position of the center of mass. To maintain the position of the center of mass. Yes or no? Not only that. Sorry? Yes, yes. I'll explain that. That's where I'm coming to. Eventually my objective is to develop a model when they move further away. Right? So by this time, see, they would have developed a velocity, this would have developed a velocity v1 to the right, this one would have developed a velocity v2 in their respective equilibrium positions. Now, when I release the two masses, what was their linear momentum? 0. When I release the two masses at C and D, their linear momentum was 0. Were there external forces acting on the system? No. That means they must have maintained their linear momentum 0 all the time. Therefore, to maintain zero linear momentum, the momentum in this direction must be equal to momentum in this direction. So m1 v1 must be equal to m2 v2, so that the net linear momentum of the system remains 0, right? So for sure, m1 v1 must be equal to m2 v2. The velocities, their respective velocities in the equilibrium positions. They arrive at the equilibrium positions together to preserve the position of the center of mass. How's that? Right? Now, from this point onwards, since they have developed velocities, this would overshoot this mark, this would also overshoot this mark, right? After some time, and do you realize that for m1 this was the state, where the spring was not elongated, so no force acting on m1, no force acting on m2. So this must represent equilibrium states of m1 and m2. Now, because of, even though there is equilibrium of m1 and m2, because of inertia they would move away. It would have developed a velocity, so they would move away further. Now, after a while, let's say m1 comes to this state, let's say state E, m1 arrives at this state E, and x1 units from its equilibrium position, and at the same instant m2 arrives at this state, and it has got displaced by an amount x2 from its equilibrium position. Have I cluttered it all, or you can visualize everything that I am writing there? Right? So, from the equilibrium state of m1, it has got displaced to the left by an amount x1 after a while. At the same time, m2 has got displaced by an amount x2 from its own equilibrium position, right? So what? Their center of mass should still be the same. So which means the disturbance caused in this direction m1 x1 must be balanced by m2 x2, yes or no? Yes, sir. To preserve the x coordinate of the center of mass. So m1 x1 is m2 x2. Yes. Now in this state, by what amount has the spring got elongated? x1 plus x2, right? So while the masses are in states E and F, at E and F, the spring has got elongated by an amount x1 plus x2. The spring has got elongated by an amount x1 plus x2, right? Isn't it? What's the spring force? The spring force would be of magnitude k times x1 plus x2 would be the magnitude of the spring force, right? And the same spring force will act on the two masses, right? So look at mass m1. The spring force acting on it would be k into x1 plus x2. And do you realize that this spring force is directed towards the equilibrium position? So it's a restoring force. It's a restoring force, right? So the restoring force acting on m1, the restoring force acting on m1 is k times x1 plus x2. That's a restoring force acting on m, right? Yes or no? And can I replace, where x1 is the displacement of m1 from its equilibrium position? x1 is the displacement of m1 from its own equilibrium position, clear? Now can I not replace x2 by m1, x1 by m2? Right? So let me do that. So k times x1 plus this x2 replaced by m1 x1 by m2. Yes or no? Which is like k by m2 into m1 plus m2 into x1. Yes or no? Therefore, the restoring force acting on M1 is proportional to displacement from the mean position, x1. The restoring force on M1 is proportional to its displacement x1 from the mean position, and therefore the motion of M1 must be simple harmonic, with this being the mean position, this being the mean position, not the amplitude. See, net force is 0 here. This is the mean position, net force 0, right? Right. So restoring force acting is this. What's the force constant for the motion? This must be the force constant K prime for the motion. The constant of proportionality between force and displacement must be the K prime for the system. Right now? No? This is only on M1. I'm talking of the motion of M1 first. Right? Whatever I say of M1 then will be true of M2. Just watch that. Okay? So this is the force constant for M1. K prime. What would be the acceleration of M1? Acceleration of M1 directed towards the mean position A1 would be the force acting on M1, K by M1 M2 into x1, right? Force divided by M1 would be the acceleration of M1 directed towards the mean position, right? Yes or no? Yes, therefore, this must be the omega square of the system. Omega square for M1. M1 executes simple harmonic motion number 1 about this mean position with omega square being this. That means with omega square being K by K into M1, I could have written this as K divided by M1 M2 by M1 plus M2. Yes or no? Where this conventionally M1 M2 by M1 plus M2 is called the reduced mass of this system. Is called the reduced mass of the system, mu. Realize that it's less than M1 as well as less than M2. So it's a reduced mass for the system. So then omega squared, omega would be root K by mu. Mu is the reduced mass of the system, right? So M1 executes simple harmonic motion. M1 executes simple harmonic motion with omega equal to root K by M1 M2 by M1 plus M2. With this being the equilibrium position, right? And M2 will also execute simple harmonic motion with this as the equilibrium position and with omega square given by M2 M1 by M2 plus M1. Replace M1 by M2 and M2 by M1. You'll get the omega for M2, isn't it? Don't reinvent the wheel. You know what I'm saying? So omega for M1 will be the same as omega for M2. The only difference is M1 will execute simple harmonic motion with this omega about this equilibrium position. M2 will execute simple harmonic motion about this position with the same omega. Root K by mu. Mu is the reduced mass of the system. Is that all right or not all right? It's okay now? And yes, see, now what about the amplitude of oscillation? Realize that this was the state where M1 had 0 velocity, isn't it? M1 had 0 velocity in this state. This therefore must have been an extreme state. Therefore A1 must have been the amplitude. This is the mean position. A1 therefore must have been the amplitude for M1. A2 must have been the amplitude for M2. And do you realize A1 plus A2 together was the total compression, where to preserve the center of mass we must have had M1 A1 equal to M2 A2. So I can solve for the amplitudes A1 and A2. Eventually, yes, that will happen. It has to go A1 units here and it has to go A2 units there. So, no, this is not an extreme state. It will go further down. This is not an extreme state. This is not a state where its velocity has become 0. This is just an intermediate state. And we figured that in this intermediate state, the restoring force is proportional to displacement from the mean position. I never said that. This is a state where the velocity has become 0. Right? Do you all understand this? Clear, na? Sounds all right? I know what you're waiting for, but you have to wait some more time. Can I wipe this off? If there were two I couldn't hear you. Two different springs. Okay. Let me tell you that. See, if there were two different springs, say joined, one with force constant K1, one with force constant K2, then these two springs essentially would be springs in series. Then that could be replaced by K equal to single spring of K equal to K1 K2 by K1 plus K2, and you could do just this again. Right? So it doesn't matter. In fact, one of the things that I need to tell you here is that this could also have been looked upon as, see, this was mass m1, this was mass m2, right? And this was their center of mass, which never changed with time, right? This was the equilibrium position of m1, this was the equilibrium position of m2, right? Now think of it like this. One could have imagined this to be as follows. Since this is a position that is not changing with time, so this point of the spring is fixed, permanently fixed. It's as if there is a wall here, it's as if there is a wall here, there is this floor here, there is a mass m1 here, this is the equilibrium position of the mass m1, and about this point P, it's as if I'm displacing it by an amount x1, then it reduces to an earlier situation, a single block system executing SHM with this point being permanently fixed to a wall. Isn't it? Huh? Yes, yes, you're right. That's exactly what I was coming to. See, now, this mass therefore is about this part of the spring only, right? Say, if this was L1 and this was L2, right? If this was L1 and this was L2, then this length L1 would be about spring constant K1, right? And the omega of this could have been looked upon as root K1 by M1. I'll tell you how to calculate K1, K2. That's a very simple issue, trivial issue. And for this part of the spring, if this is fixed, it's as if there is a single block of mass M2 and this length being L2, this being K2, right? This being K2. This mass M2 would be root K2 by M2. Right? Equivalently, now how to calculate K1 and K2? See, do you remember? K of a spring is given by AY by L. I've discussed this, area of cross section, Young's modulus divided by the length of the spring. Have I discussed this in the past? Right? So, K into L is A into Y. हाँ बोल भाई क्या बोल रहा है हाँ right so since whether I take this part of the spring or I take this part of the spring, I'm talking of the same A and the same Y. So K1 L1 must be equal to K2 L2 precisely. Yes or no? Right? And if this is the center of mass, the moment of this mass about the center of mass must be equal to moment of this mass about the center of mass. So can I not say m1 L1 is m2 L2? That's a dictum on the center of mass. About the center of mass, I told you the moments of the two masses must be the same on either side of the center of mass. m1 L1 must be equal to m2 L2. Now if I divide this by this, k1 by m1 is k2 by m2. Although, you know, I can calculate k1 and k2. I can calculate k1 and k2, but do you realize k1 by m1 is k2 by m2? So omega 1 must be equal to omega 2. Isn't it? Isn't it? Which is what we obtained after so much of hard work, right? Isn't it? And you can solve for k1 and k2 and you will obtain where L1 plus L2 is the total length of the spring, and you will be able to obtain that omega would be root k of the original spring, where see this all of this is also equal to k into L, where L is L1 plus L2. Do you realize that? This was the entire spring k and had a length L. So that's also equal to k into L. So you can solve for k1 and k2 using these conditions in terms of k, isn't it? And plug into this, you will get omega equal to root k divided by mu m1 m2 by m1 plus m2. Right? That's another way of looking at the entire system. Do you get me right on this?
Yes.
Right now? Seems all right so far? Are you tired? No, then we'll have two things. See, if you were tired, I would have had one thing. If you are not tired, then two things. No, if you are not assimilating, I'll stop. Very fatigued? Saturated? No? Yes?